The next part is very easy. What we will do is actually use the previous functions that we have defined so that we can recover each one of these values. And this function will have a lot of outputs. All of these outputs are actually outputs from previous functions. It's just that inside this function we will call the previous functions. But one of great interest is this one. It is equilibrium. If equilibrium is 0 or very close to 0, that means that the neutral axis is correct. We will use this later because this function will be useful to actually find the real neutral axis and the value of c. So we have a lot of inputs as we have a lot of functions inside. We have height of the head, of the wave, the y of the slices, the strain at the top, an initial guess of the neutral axis, and all these other variables that we have defined so far. Okay, so again, we just call the previous functions. We call get EPS elastic, get the stress and strain. We call get steel def. We call get FS bilinear model. With that, we can call get force on concrete, and then we can call get force on steel. So now, this variable has the force on each one of the elements of concrete, and this variable has the force on each one of the layers of steel. Now, to reach equilibrium, the sum of all the force of the elements plus all the layers of steel should be equal to 0. Okay, that in the case that the neutral axis position is correct. So this equation, this function returns this variable equilibrium. It might be 0, it might not be, but then we will use the next function combined with this function to calculate the actual neutral axis. So this function has the name find c, and we will have the same inputs as the previous function since we are going to call the previous function. And then I have defined here the bisection method. If you have taken numerical methods for engineers, you might be familiar with this, but if not, I will go over it. Okay, so in bisection method we define two limits. One of them is going to be a value close to 0, could be 0, and another limit is going to be the total height of the web. Because the neutral axis must be between the top and the bottom of the beam. We define a tolerance value for convergence because since we're doing things numerically, we might not find the exact equilibrium point, but a point where this value equilibrium is really close to 0. We also define a maximum number of iterations so that we don't go until infinite in case we don't have convergence. And then the bisection method begins here. We define a flag value, which is a temporary value, just to be able to enter to this conditional loop. And then we also define a number of iterations. This is not completely, well, no, this is necessary, sorry. Okay, this is to have a control over the final number of iterations, and let's go over it. So this conditional is repeated if the absolute value of the variable equilibrium is greater than this value of tolerance, and if the number of iterations is lower than the maximum number of iterations, in this case defined as 10,000. So on each step in the loop, what we do is to update the number of iterations, and in bisection method, what we do is to calculate C. C is the average within the between the the left and the right limit where we think the value of C is. So this is a guess of the value C of neutral axis. We are saying that it is in the half of these two limits. Now, this is something related to the bisection method. So what we do is to calculate the equilibrium in the left side. So what we do is to call the function calculate beam, which is this one, and the value of the initial of the neutral axis. Remember that here we had a C0, I think. Yeah, we had a C0. Instead of using C0, we are going to use the value of the left value. And the right side is calculated with the right value, which is in this case the bottom of the beam. And then the value of equilibrium is when we calculate this with the new guess of the neutral axis. In this case, it's going to be C. So now, again, this is from the bisection method. If the left side times the return of the new guess is less than 0, which means they have opposite signs, then we have to update the right limit. And if that's not the case, what we have to update is the left limit. And we repeat this operation until we have an equilibrium which is less than this value of tolerance. So in case we overpass the maximum number of iterations, what we do is to plot an error saying that the equilibrium was not reached. But yeah, basically what this function do is to call all the previous functions to find the value of C. On Excel, you do this very easily by using some goal seek, for example. But here in this case, I use this bisection method just because I remember my math methods for engineer class and I wanted to apply it. But if you find a better method to calculate this neutral axis, please use it, because I feel this is kind of complicated. And if you don't want to really think how to find this neutral axis, feel free to copy this code, and it should find the neutral axis. Okay, so now after that function, we have the real neutral axis. So the next step is just to calculate the nominal moment. So this function get m will calculate the nominal moment. The inputs will be the real neutral axis, the forces on the concrete, the position where the forces are applied, the forces on the steel, and the position of the centroid of each one of the layers of steel. So we begin by calculating the arms for each one of those forces of concrete, simply by doing neutral axis minus this vector. We also calculate the arms of steel, which is the neutral axis, minus these coordinates. And then we calculate the moments for each one of the elements of concrete. We do that by doing the arms times the force. We divide by 12 so that we have these moments in keep fit. We do the same for the moments in steel. We multiply the arms times the force, divide by 12, and then we return that as keep fit. And then we sum all these moments. We sum the moments of concrete plus the sum of the moments in steel, and we calculate the total moment in the beam.